Welcome to Night Chemistry, your midnight laboratory of calm. Tonight, we dive into the essence of matter itself, exploring the silent stories hidden within one of nature's fundamental building blocks. Before we begin, let's invite a deep, steady breath together. Breathe in gently to the count of 4. 1, 2, 3, 4. Hold softly. 1, 2, 3, 4. And now exhale slowly. 1, 2, 3, 4, 5, 6. Feel the space around you soften. Let your body begin to settle. Your shoulders ease down, your jaw unclenches, and your hands rest quietly. Let's take another breath together. Breathing in calm and quiet. 1, 2, 3, 4. Holding gently. 1, 2, 3, 4. And slowly exhaling. 1, 2, 3, 4, 5, 6. Now imagine a dark canvas of night. No stars, no sounds, just deep silence. Through that stillness, tiny particles begin to drift. They move gently like the last embers from a fire. These are ancient pieces of carbon, born inside stars, released into space, waiting. This is not just dust. It is structure. It is memory. It is potential. Now picture the periodic table before you. In the second row, at number 6, you see the letter C. It may look simple, but it stands for something that holds life together. Let your breath return to its natural rhythm. Inhaling gently, exhaling fully. The same carbon that forms diamonds also shapes your cells. The same carbon that burns in a flame is part of every breath you release. You are not separate from this element. It is in your bones. It is in the air. It is in the food that nourishes you and the thoughts you carry. Now picture 3 forms before you. First, a diamond shining with cold fire. Second, a stick of graphite, soft and dark, ready to mark a blank page. Third, a faint swirl of smoke from a candle, rising and fading. All 3 are carbon. All 3 carry the same atomic heart. Each shows a different face of the same quiet force. Now breathe once more, and let go of the tension in your chest. As your lungs rise and fall, feel yourself joining the rhythm of something older than words. Imagine a forest under moonlight. The trees stand silent, their trunks built from carbon reaching upward. The soil beneath them is rich with fallen leaves, each returning carbon to the earth. Even the animals sleeping among the roots carry carbon within every heartbeat. It binds together the living and the dead, connects breath and stone. It waits quietly in every cell, holding the pattern of life. Let yourself rest in that thought. You are not apart from this pattern. You are part of it, breathing, thinking, remembering, releasing. You are ready now. The journey begins. Discovery 1.1. Who discovered the element? Long before it was called an element, carbon was already part of every life. It glowed in the center of the fire. It stained the palms of artists drawing with charcoal on cave walls. It blackened the ceilings of temples and huts. Carbon was the silent companion of humanity. But for most of history, no one knew carbon as a single thing. People spoke of charcoal, coal, soot, and diamond as if they were entirely separate. In truth, all of them were simply different forms of carbon. Thousands of years ago, ancient people burned wood to cook and stay warm, never realizing they were working with a fundamental element. When black rock was pulled from the ground and fed to furnaces, when artists sketched with burnt sticks, they were all holding carbon in their hands, though they had no word for it yet. In ancient Greece, philosophers like Theophrastus described a black mineral called anthrax, a kind of coal. They knew it could burn and smelt metal. But to them, the world was made of 4 elements: earth, water, air, and fire. There was no periodic table, no atoms, no understanding of chemical identity. And yet, behind every flame, every glowing ember, every breath of smoke, carbon waited to be recognized. During the Middle Ages, alchemists ground charcoal into fine powder, mixing it with mercury and sulfur in their pursuit of transformation. They believed charcoal had power to change one substance into another. They were not wrong. They just didn't know that charcoal is mostly carbon, and carbon is transformation itself. But the first to see carbon clearly as an element, something fundamental, indivisible, and unique, was the French chemist Antoine Lavoisier. His experiments in the late 1700s helped science name what had always been there. Lavoisier understood that something invisible was happening in every fire. When he measured the weight of burnt wood or diamond, he found that the loss of mass was not disappearance, but change. The missing matter had become gas. The gas was heavy, acidic, and capable of turning lime water cloudy. It was carbon dioxide, the breath of carbon escaping into the air. And so, Lavoisier became the one to give carbon a name. From the Latin carbo, meaning charcoal. He listed it among the chemical elements, alongside oxygen and hydrogen. From that moment, carbon was no longer a mystery. It was a pillar of chemistry. 1.2. When it was discovered, the discovery of carbon as a chemical element came not in a single flash of light, but in a slow awakening of thought. The year was 1789. Antoine Lavoisier published his book Elements of Chemistry, a work that redefined how people thought about matter. In that book, carbon appeared for the first time as a named, distinct element. But the journey to that moment began centuries earlier. From ancient times through the Enlightenment, carbon was known by many faces: coal, soot, charcoal, and the brilliant hardness of diamond. But science had not yet connected the dots. People believed they were working with many different materials. No one suspected they were all built from the same invisible atoms. The alchemists had used carbon in the form of charcoal for hundreds of years. They saw its ability to change substances and intensify fire. But without the language of elements, they could not name what they held. In the 16th and 17th centuries, early chemists began to measure and observe more carefully. One of them was Robert Boyle, who questioned ancient theories and laid the foundation for experimental chemistry. He studied gases and reactions, but even he did not recognize carbon as a single, essential element. The true shift happened in the 18th century, during the Chemical Revolution. It was Lavoisier who made the final connection. In a famous experiment, he placed a diamond, a precious crystal believed to be indestructible, inside a sealed glass vessel. He focused sunlight through a lens, heating the diamond until it vanished. No smoke, no ash, just a gas. That gas was carbon dioxide, the same gas formed when wood or charcoal burned. The conclusion was unavoidable. Diamond, coal, and charcoal were not different materials. They were all carbon wearing different masks. This was the beginning of a new understanding. That a single type of atom could exist in multiple forms. That a black lump of coal and a shimmering jewel could be the same element, simply arranged in different ways. From that moment, carbon stood among the elements. Known, understood. 1.3. Conditions and circumstances of discovery. The discovery of carbon as an element did not happen in a grand palace or under a microscope. It happened in a laboratory of glass, fire, and patience. In a world lit by candles, where ideas were weighed as carefully as powders on brass scales. Antoine Lavoisier's lab was simple: glass tubes, balance scales, wax-sealed flasks. And yet, in that quiet room, he reshaped the foundations of chemistry. He did not discover carbon in the way one finds a new island. He recognized it. He gave it a name and a number. He showed the world that the dark and the bright, the rough and the polished, were all made of one thing. He called it carbon. Element number 6. Silent, essential, everywhere. Lavoisier's methods were revolutionary because he believed that what cannot be seen can still be measured. He captured gases in sealed vessels. He noted their weight. He analyzed their effects. When he burned charcoal, a gas appeared. When he burned diamond, the same gas appeared. And that gas turned lime water cloudy, indicating the presence of carbon dioxide. This was not alchemy. This was evidence. Lavoisier wrote it all down in precise language. He added carbon to the growing list of elements, and in doing so, he changed how science understood the world. But even after Lavoisier, carbon continued to surprise. In the 19th century, scientists discovered that carbon atoms could link together in long chains and complex rings. This gave rise to a new field, organic chemistry, built entirely around carbon. They learned that carbon is the backbone of life's molecules: sugars, fats, proteins, DNA. Everything living is made, in part, from this one quiet element. Later still, in the 20th century, researchers uncovered new forms of carbon. Tiny hollow spheres called fullerenes, one-atom-thick sheets called graphene, cylindrical structures stronger than steel, called nanotubes. All of them made from the same building block, carbon atoms. And even now, in the 21st century, carbon continues to shape our future. It helps filter water. It forms batteries. It lies at the heart of climate change, and at the center of every living cell. From the soot on your fingers to the breath in your lungs. From the sparkle on a ring to the roots of a tree. From a candle's smoke to the bones beneath your skin. All of it contains carbon. It is the element of memory and of fire, the storyteller of life, the silent frame behind every living thing. So when we speak of its discovery, we are not just talking about a gas or a rock or a number on a table. We are talking about the moment when we finally understood that carbon is not just part of the world. Carbon is what the world is built from. Properties and Presence. 2.1. Key physical and chemical properties of carbon. Take a slow breath in and picture a single carbon atom. 6 protons in the nucleus, 6 neutrons close beside them, 6 electrons moving in 2 quiet shells. Small, balanced, ready to build. The outer 4 electrons are like open hands, eager to clasp neighboring atoms. That readiness makes carbon the great connector of the periodic world. Now imagine carbon wearing three very different coats. A diamond. Every atom grips four others in a rigid lattice that stretches in all directions. Light crosses that lattice, bends and scatters, giving the familiar sparkle. Diamond is the hardest natural material we know. Strike it with steel and steel gives way. It melts only under pressures found deep inside Earth. And it carries heat faster than copper wire. A graphite. Here carbon atoms link in flat hexagonal sheets that slide one over another like winter skates on ice. The bonding between layers is gentle, so the sheets shear away with the lightest touch. That softness lets pencil graphite leave dark trails across paper. Yet within each sheet, the bonds are strong and the electrons roam freely, allowing graphite to conduct electricity. Amorphous carbon, soot, charcoal, lampblack. Atoms gather in tangled clusters with no long-range order. This disordered form is excellent at trapping molecules. When powdered and activated, it filters toxins from water and draws poisons from a troubled stomach. These three faces share common traits. The color ranges from clear to deep black because carbon's electrons absorb and reflect light in many ways. Carbon neither melts easily nor boils kindly. It prefers to sublimate, turning straight from solid to gas at temperatures above 3700 Kelvin, which is hotter than most furnaces can reach. Chemically, carbon moves gracefully between oxidation states. In methane it sits at -4, surrounded by hydrogen's embrace. Burn that methane in air and carbon leaps to +4, exhaling as carbon dioxide. Between those extremes lie carbon monoxide at +2, formic acid at +2 as well, and countless organic molecules where carbon holds a charge closer to zero. These shifts power life and industry alike. Combustion of carbon-rich fuels warms homes and drives turbines. Carbon's reversible redox dance delivers electrical current inside lithium-ion batteries. Carbon also forms carbides with metals such as iron, tungsten, and silicon. Cementite hardens steel. Tungsten carbide shapes drill bits that bite through stone. Silicon carbide sparkles in sandpaper and endures in high-temperature reactors. Under specific conditions, carbon bonds only to itself, curling into fullerenes shaped like tiny soccer balls, stretching into graphene one atom thick, or rolling into nanotubes stronger weight for weight than any steel cable. Each of these nanostructures conducts heat and electricity with astonishing speed, yet weighs next to nothing. Engineers now knit graphene sheets into flexible circuits, sew nanotubes into composite wings, and sprinkle fullerenes into solar cells that catch sunlight more efficiently. Even isotopes reveal carbon's depth. Carbon-12 is stable and makes up 98% of natural carbon. Carbon-13, also stable, sits at about 1%. Carbon-14 forms high in the upper atmosphere when cosmic particles strike nitrogen. Carbon-14 decays slowly, counting down the years in bone, wood, and canvas. Thanks to that silent clock, we can date the age of Pharaoh's linen, measure the last breath of Pleistocene mammoths, and trace ancient fires in Stone Age hearths. All these traits, hardness and softness, order and tangle, stability and gentle decay, spring from one truth. Carbon's 4 valence electrons allow it to bond in an astonishing variety of ways. That simple balance, 4 hands open, lets it weave chains, rings, nets, and frameworks of every length and shape. No other element matches this architectural range, and none underwrites as many stories. 2.2. Its location in the periodic table. Picture the periodic table like a grand library of matter. Walk to the second row, the small shelf where elements with only 2 electron shells reside. Move 5 columns from the left margin. There you find square number 6, the quiet seat of carbon. The family it heads is called group 14, sometimes the carbon family, shared with silicon, germanium, tin, and lead. What does that placement tell us? A period 2 means carbon's electrons fill just 2 shells, keeping its atomic radius compact and its bonding angles tight. A group 14 means 4 valence electrons, neither hungry nor satisfied, free to share covalent bonds generously. Being a p-block non-metal gives carbon moderate electronegativity, high enough to hold electrons in polar bonds, yet low enough to release them when paired with stronger partners like oxygen. This middle stance enables carbon to form both non-polar hydrocarbons that float on water and polar sugars that dissolve in it. In periodic trends, carbon sits at the crossroads. To its left, boron leans toward metal behavior in alloys, yet remains mostly metalloid. To its right, nitrogen gains one more proton, pulls electrons closer, and moves into the world of gases. Down the group, silicon echoes carbon's bonding but grows larger, slower, preferring to build rocks rather than living cells. Carbon, small and nimble, bridges these extremes. It is the hinge between life's complexity and Earth's minerals. 2.3. Its prevalence and natural sources in nature. Now breathe in and follow carbon on its endless journey. In the cosmos, every carbon atom in your body was forged in the heart of a giant star. Inside stellar furnaces, 3 helium nuclei, each with 2 protons, fuse in a dance called the triple alpha process. In the blink of cosmic time, they merge into one nucleus of carbon-12. When the star dies in a supernova, it hurls carbon dust across space. That dust drifts through nebulae, settles into new solar systems, and becomes part of planets, comets, meteorites, and eventually living cells. Astronomers estimate that carbon ranks as the 4th most common element in the Milky Way, after hydrogen, helium, and oxygen. In Earth's crust and mantle, carbon laces through limestone cliffs as calcium carbonate, forms marble high in the Alps, hides in crude oil trapped under seabeds, and rests as coal seams that snake beneath valleys. Graphite veins weave through metamorphic rock in Canada, India, and Madagascar. Diamonds ride to the surface in kimberlite pipes, volcanic channels that rooted miles deep in the mantle before erupting. In the atmosphere, as carbon dioxide, carbon makes up only about 420 parts per million of modern air. That small fraction wields large influence, trapping solar heat and steering climate. As methane, carbon appears in concentrations measured in parts per billion, yet warms the planet even more effectively per molecule. In the stratosphere, carbon dioxide helps radiate heat back into space, balancing the global energy budget. In the hydrosphere, the oceans store 50 times more carbon than the air. Waves absorb carbon dioxide, which reacts with water to form bicarbonate and carbonate ions. Tiny plankton build calcium carbonate shells, then rain down as marine snow, carrying carbon to ocean depths where it may rest for centuries. Coral reefs, chalk cliffs, and deep-sea ooze all owe their existence to this oceanic carbon bank. In the biosphere, every leaf, feather, hair, and lung cell is built on carbon frameworks. A typical adult human weighing 70 kilograms carries roughly 15 kilograms of carbon, arranged in sugars that power muscles, lipids that cushion organs, proteins that fold into enzymes, and nucleic acids that store memory. A towering oak holds nearly half its dry mass in carbon captured from air, locked away in cellulose and lignin. Microbes beneath forest floors cycle carbon faster than any factory, decomposing fallen leaves into soil nutrients and carbon dioxide. In the technosphere, industrial stacks send gigatons of carbon skyward each year as carbon dioxide. Plastic bottles, nylon threads, epoxy glues, and asphalt roads all rely on carbon drawn from ancient hydrocarbons. New carbon materials now reinforce jet wings, purify medical drugs, strengthen concrete, and store electric charge in compact supercapacitors. Even digital life depends on carbon. Every silicon chip is encased in epoxy resin, every fiber optic cable is shielded with polymer cladding, every smartphone screen glows behind a thin carbon-based adhesive layer. Together these reservoirs form Earth's carbon cycle, a grand circulation measured in breaths and millennia. Volcanoes and weathering rocks release carbon. Photosynthesis fixes it into living tissue. Respiration and decay return it to air. Sediments bury it for ages. Human activity now tips that balance, drawing fossil carbon and releasing it in decades rather than eons. Understanding carbon's presence is thus not only academic, it is vital to guiding climate, food, and energy for generations ahead. Brief pause. Take one more breath and notice the invisible thread of carbon moving in and out of your lungs, the same element drifting through forests, oceans, and clouds. A single atom may leave the soil as carbon dioxide, cross an ocean, glide over a city, slip into your bloodstream, and 6 months later rest in a sunflower seed. Such is the reach of carbon, ever-present, ever-moving, patient, and persistent. In diamond it endures for billions of years. In graphite it marks a thought in the span of a heartbeat. In carbon dioxide it rises on your exhale, swirling into night air under the quiet stars. This is carbon, flexible in bonding, central in life, spread across the universe, yet gathered for a moment inside each gentle breath you take. Role in the universe. 3.1. The birth of carbon inside stars. Close your eyes for a moment and imagine the very young universe. It is hot, bright, and simple. Hydrogen drifts in great clouds. Helium follows, light as song. Nothing heavier can yet exist. That changes when the first giant stars kindle their cores. In those furious furnaces, temperatures climb to hundreds of millions of degrees. At such heat, 3 helium nuclei can merge in a brief, delicate sequence called the triple alpha reaction. 2 helium nuclei form a short-lived beryllium. Before it falls apart, a third helium arrives and locks in place, creating carbon-12. This tiny act, repeated countless times within countless stars, seeds the cosmos with carbon. Each fusion event releases energy that pushes back against the star's inward gravity, letting the star shine. Carbon becomes a silent architect, stabilizing the stellar core while opening the door for heavier elements. When a massive star exhausts its hydrogen and helium, it swells into a red supergiant. In the deeper layers, carbon now fuses with helium to form oxygen, neon, and magnesium. But not all carbon is consumed. Outer shells rich in carbon are blown into space when the star sheds its atmosphere as a glowing nebula or explodes as a supernova. Billions of tons of carbon dust spread outward at thousands of kilometers per second. They drift for centuries, cool, and condense into grains small as smoke. These grains mix with interstellar gas, coloring distant nebulas with faint red-brown hues. Without that violent shedding, there would be no carbon for planets, no carbon for life, no carbon for the breath you just took. Every carbon atom in your blood was born in a star's heart and flung across light years before settling into the cloud that became our solar system. 3.2. The journey of carbon across galaxies and worlds. Now picture the Milky Way as a rotating spiral of starlight and dark lanes. Within those dark lanes, carbon rides in many forms. Some atoms travel alone as carbon monoxide, one of the most common molecules in space. Astronomers map newborn stars by tracing this gas with radio telescopes. Other atoms gather in large flat molecules called polycyclic aromatic hydrocarbons. These drifting sheets absorb ultraviolet light and re-emit soft infrared glows, painting nebulae in subtle colors invisible to human eyes but clear to space observatories. While clouds of gas collapse into new stars, carbon grains act as efficient cooling agents. They radiate away heat, allowing the cloud to contract further until nuclear fusion ignites once more. In that way, carbon from earlier stars quietly guides the birth of the next generation. Galactic chemical evolution depends on such recycling. After billions of years, each cycle leaves the spiral arms richer in carbon than before. Today, astronomers estimate that roughly one atom in every 10,000 within the interstellar medium is carbon, a surprisingly generous share for a heavy element. Closer to home, carbon fills comets as frozen carbon dioxide and carbon-rich dust. When early Earth was still molten, such comets and carbonaceous asteroids rained down by the million. They delivered graphite, simple sugars, amino acids, and reactive cyanides. Laboratory experiments show that ultraviolet light shining on these ingredients can form nucleobases, the letters of RNA. Carbon therefore arrived not only as raw matter but as preliminary script, ready to help life compose its first sentences. Step onto Mars in your mind and feel the chill of a thin pink sky. Carbon dioxide dominates its air, while carbonate minerals mark places where ancient water once flowed. On Venus, carbon dioxide wraps the planet in a dense, hot cloak that turns sunlight into a pressing furnace. On icy worlds like Triton, frozen carbon monoxide blankets the ground. Around stars richer in carbon than our Sun, theorists predict entire planets of carbide rock and diamond mantles, worlds where mountains might sparkle and rain could fall as liquid hydrocarbons. Some aging stars become true carbon stars. Their convective layers dredge up newly made carbon from the core and push it into the atmosphere, turning the whole star ruddy. Astronomers can measure this carbon bloom in spectra that show strong absorption lines for molecules such as C2 and CN. Each carbon star is a lighthouse signaling that fresh carbon is sailing out to fertilize space once again. Even black holes, often portrayed as cosmic endings, spread carbon indirectly. When two neutron stars merge, they fling heavy elements in every direction. Gamma ray bursts follow, and expanding shells mix carbon with gold, platinum, and other forge-born riches. These blasts seed future nebulae, ensuring that carbon keeps company with a full orchestra of elements. 3.3 Cosmic Mysteries and the Future of Carbon. Although carbon seems well known, the universe still hides many of its secrets. Astronomers have detected spectral hints of complex carbon chains floating between stars, but laboratory confirmation remains hard. Some of these molecules might be precursors to life, carrying reactive sites that, under gentle starlight, could knit together into sugars or nucleotides. If that chemistry progresses on damp dust grains or within warm comet interiors, then life's ingredients might be widespread. Carbon would not merely allow life. It would encourage it. Another mystery lies in the balance of carbon isotopes across galaxies. Carbon-12 and carbon-13 form in slightly different stellar conditions. Measuring their ratio in distant clouds helps map star formation history. Yet observations sometimes disagree with models. Factors such as stellar rotation, magnetic fields, and binary interactions may change how much carbon each generation of stars returns to space, and astronomers are still refining those calculations. Looking ahead billions of years, the Milky Way will merge with the Andromeda Galaxy. Their combined gas will spark new waves of star formation. Carbon carried by both galaxies will mix, perhaps raising the overall metallicity of the merged system. The night skies of future planets may glow with great swaths of newborn stars, each promising new carbon cycles. On smaller timescales, humanity is already influencing carbon's cosmic story. Our telescopes search for methane and carbon dioxide on exoplanets, hoping to read atmospheric fingerprints that hint at biology. In the next decade, space observatories may capture direct spectra of rocky Earth-like worlds. A disequilibrium mix of carbon compounds on a distant planet could be the first evidence of life beyond our solar system. Far in the future, when stars like our Sun exhaust their fuel, they will shed planetary nebulae rich in carbon. The leftover cores will cool into white dwarfs, then into black dwarfs, silent spheres of crystallized carbon and oxygen. Over quadrillions of years, those spheres may crystallize almost fully, turning into gigantic diamond hearts drifting through a darkened cosmos. Carbon will outlive starlight. It will remain in black dwarfs, rogue planets, and cold dust even when galaxies fade into faint smudges. The element that carried the warmth of your body and the pattern of your thoughts will continue its patient drift, perhaps to kindle new chemistry in a reborn universe or to rest as frozen jewels in endless night. Closing reflection. Breathe slowly once more. Feel the strand of carbon atoms that forms your backbone, the carbon dioxide leaving your lungs, the molecules of graphite in the device from which you listen. Those atoms traveled from a red giant through a supernova, into a molecular cloud, into a planet, into food, and finally into you. When you exhale, some of them return to the air, ready to rise on winds, cross oceans, feed leaves, or drift upward to the very edge of space. Carbon is the ink with which the universe writes its many stories. It forged stars, darkened nebulae, built planets, and seeded life. It will shape worlds we have not yet seen and outlast suns we have not yet named. And in this quiet moment, in the rhythm of your own breathing, it reminds you that matter never stays still. It journeys, learns, remembers, and begins again. As the night deepens, allow that idea to settle. You are part of a cosmic carbon cycle billions of years old and far from finished. Let each slow inhalation connect you to stellar hearts. Let each calm exhalation send your own stardust back into the waiting dark. in life. 4.1. Carbon in the human body. Take a gentle breath. Feel your chest rise, feel it fall. Each movement is powered by chemistry, and at the heart of that chemistry is carbon. The average adult human weighs about 70 kilograms and carries close to 15 kilograms of carbon. That single element forms the framework of nearly every biological molecule inside you. Molecular architecture. Begin with proteins. Every strand of muscle fiber, every antibody scanning your blood, every enzyme guiding reactions in your cells relies on chains of amino acids. Each amino acid has a carbon backbone, a string of linked atoms that folds and turns in three-dimensional space. Those folds determine whether an enzyme speeds up digestion in your stomach or repairs DNA in your nucleus. Without carbon's 4 open bonds, none of those shapes could hold. Move to carbohydrates. Glucose, the simplest blood sugar, is a ring of 6 carbon atoms. As you walk, think, and dream, mitochondria in your cells snap apart that ring, releasing energy that drives every heartbeat. When 2 glucose molecules join, they form maltose. When hundreds join, they become glycogen, curled and coiled in liver and muscle tissue. Carbon's ability to link endlessly lets your body store fuel safely, ready for the next burst of effort. Consider lipids. Fatty acids are long carbon chains ending in a gentle hook of oxygen and hydrogen. They slip together to build cell membranes, fluid barriers that flex yet hold fast, separating the chemistry of life from the chaos outside. They insulate nerves, cushion joints, and carry vitamins that soothe vision and bolster immunity. Look at nucleic acids. Carbon forms the spine of DNA and RNA. 5 carbon sugars called ribose and deoxyribose link together, each holding a nitrogenous base like adenine or cytosine. Those bases record genetic letters, and carbon keeps the letters in order. When a cell divides, carbon rings unzip, duplicate, and rezip, ensuring that the map of a whole person travels safely into the next generation. Metabolic flow. At rest, your body exhales about 1 kilogram of carbon dioxide each day. That gas is carbon's exit ticket after glucose has been burned. In skeletal muscle, carbon atoms from lactic acid move back into the blood to be processed by the liver, a quiet recycling system that keeps pH steady. In red blood cells, carbon dioxide binds loosely to hemoglobin, hitching a ride from tissues to lungs. There it meets air rich in oxygen and trades places, continuing the cycle of breath. Carbon is essential in hormone chemistry. Cortisol, the stress signal, is a 21-carbon steroid that rises with sunrise and falls with night. Estrogen and testosterone differ by only tiny shifts in carbon skeletons, yet those shifts guide growth, mood, and reproduction. Melatonin, the sleep messenger, is crafted from carbon rings derived from the amino acid tryptophan. When darkness deepens, the pineal gland releases melatonin, carbon signals drift into blood, and eyelids grow heavy. Carbon also partners with micronutrients. The iron in hemoglobin sits in a carbon-rich porphyrin ring. Vitamin B12 surrounds its cobalt ion with 4 carbon-nitrogen rings joined together. Chlorophyll in plants mirrors that design, but swaps cobalt for magnesium. This shared architecture hints at the unity of life. Plants and animals both rely on carbon scaffolds to shepherd metal ions exactly where they are needed. Bone and connective tissue. Calcium phosphate crystals strengthen bone, yet they are woven into a lattice of collagen, a triple helix of carbon-rich protein. That helical design prevents bones from shattering under everyday impacts. Carbon-based glycosaminoglycans in cartilage absorb shocks in knees and spine. Elastin in skin and arteries relies on flexible carbon chains that stretch and spring back, allowing a pulse to surge without tearing vessels. Neural sparks and senses. Every thought travels along neurons insulated by myelin, a sheath rich in carbon lipids. Neurotransmitters like dopamine and serotonin carry carbon rings that dock into carbon-lined receptor pockets. In the retina, vitamin A derivatives with long carbon tails twist when struck by a photon, triggering the first event in sight. Carbon builds the pigments that let you see color, read words, recognize a friend. Carbon is not simply present in the human body. It is the blueprint, the scaffolding, the fuel, the courier, and the historian. It holds the story of every heartbeat you have ever felt and every memory you will keep. 4.2. Carbon across all other living organisms. Shift your attention outward. Picture a forest at dawn. Mist curls above a carpet of moss, and every leaf holds a thin film of dew. From towering oaks to the tiniest lichen, life depends on carbon arranged in endless variation. Plants and photosynthesis. In the green cell, carbon dioxide slips through pores called stomata. Inside, chloroplasts capture sunlight with chlorophyll, a carbon-rich pigment that absorbs red and blue wavelengths. Light energizes electrons, splitting water and releasing oxygen. Then begins the Calvin cycle, where the enzyme rubis-CO attaches carbon dioxide to a 5-carbon sugar. Within seconds, the molecule splits, rearranges, and eventually forms glucose. That glucose becomes cellulose for trunks, starch for seeds, nectar for pollinators. Every tree ring is a diary of carbon fixed from air, one line for each growing season. Some plants in hot, dry climates follow a different path, called C4. They trap carbon dioxide at night in 4-carbon acids, then release it during sunlit hours when stomata can remain closed. This method saves water while still feeding carbon into sugar. In succulents and cacti, crassulation acid metabolism stores carbon overnight in malic acid, releasing it by day. Evolution keeps inventing new ways to shepherd carbon toward life. Fungi and decomposition. Beneath leaf litter, fungal hyphae weave fine networks. They excrete enzymes that crack lignin and cellulose, freeing carbon compounds locked away in wood. As they absorb sugars, they trade nutrients with plant roots in a symbiosis called mycorrhiza. Forests owe their health to this carbon economy in the soil. Without fungal collaborations, carbon would remain trapped in fallen trunks, and soils would starve of nitrogen, phosphorus, and potassium. Microorganisms. Cyanobacteria float in sunlit water, capturing carbon dioxide and releasing oxygen long before plants evolved. In oceans, colossal blooms of phytoplankton fix half the planet's carbon each year. When they die, their carbon-laden bodies sink, carrying organic matter to deep water where it can rest for centuries. Some bacteria thrive without sunlight at hydrothermal vents, using carbon dioxide and hydrogen sulfide to build their cells in total darkness. Methanogens in wetlands and ruminant stomachs convert carbon dioxide to methane, completing another branch of the carbon loop. Animals great and small. Insects craft chitin, a carbon-based polymer, to shield their bodies. Birds weave carbon fibers in keratin to form feathers, light yet strong. Fish store carbon in scales and collagen fins. Whales carry tons of carbon in bone and blubber. When they die, their sinking bodies deliver deep-sea ecosystems decades of nourishment. Coral polyps build reefs from calcium carbonate, exhaling it into intricate skeletons. Reefs lock away carbon while hosting a quarter of all marine species. When ocean chemistry shifts and carbon dioxide rises, carbonate ions become scarce, and corals struggle to build. Carbon links even ecological fragility to atmospheric change. Interconnected cycles. Consider a single carbon atom exhaled by a child playing on a summer lawn. The wind carries it to a maple leaf. Photosynthesis grabs it, turns it into glucose, which joins cellulose in growing bark. Winter arrives, the leaf falls, microbes digest it, releasing carbon dioxide into a pocket of soil. A burrowing worm respires that air, sharing the carbon back with the atmosphere. Days later, the atom could enter a raindrop, slip into a stream, nourish algae, be eaten by a mayfly larva, then by a trout, then by an eagle, and finally return to the sky once more. A simple atom on a journey lasting years, crisscrossing kingdoms of life. Across savannas, herds of wildebeest graze, converting carbon in grass into muscle and motion. Their wastes fertilize soil, feeding termites that raise mounds of carbon-rich humus. Wildfires sweep the plain, turning grasses into soot and carbon monoxide. Rain returns, seeds sprout, and the carbon story begins again. In the Arctic, mosses trap carbon in permafrost. Locked away for millennia, it threatens to re-enter the air as methane if ice melts. High above the Arctic Circle, lichens fix carbon slowly under weak sun, painting rocks with pale crusts that testify to patience. Life is a grand ledger of carbon. Every living system borrows atoms, spends them on growth and motion, then returns them so another organism can use them. The element moves in circles, yet the pathways are never the same. Diversity rests on carbon's flexibility, on its talent for weaving strong bonds in countless patterns. A quiet, closing thought. Let one more calm breath fill your lungs. Sense the carbon entering, wrapped in oxygen. Know it once rode inside a distant leaf, a coral reef, perhaps a dinosaur bone. Now it supports the electrical whisper of neurons behind your eyes. In a minute you will release it back to the air, and its voyage will continue. Carbon in the human body, carbon in forests, carbon in sea foam and mountain stone. One element, many homes eternally traveling. Hold that idea as night deepens. Feel yourself part of a living world bound together by carbon threads, each breath stitching you into the endless fabric of life. May that thought settle softly as you drift, ready for rest, cradled by the quiet power of carbon. Practical applications. 5.1. Medicine and human health. Take a slow breath and picture a modern clinic awash in quiet light. Carbon stands everywhere in silent service, caring for bodies and restoring calm where pain once lived. Activated charcoal is perhaps the oldest medical use of carbon. Charred coconut shells or hardwoods are heated with steam until tiny pores open like a sponge. 1 teaspoon holds a surface area larger than a football field. When a patient accidentally swallows poison, nurses mix this jet-black powder with water. The slurry travels through the stomach, trapping toxins in countless microscopic pockets. The carbon never enters the bloodstream but carries danger away for safe removal, saving lives each day in emergency rooms worldwide. Move to the intensive care ward. Here machines hum, pushing air into fragile lungs. The breathing circuits are lined with carbon fiber-reinforced plastics that deliver strength without weight, resisting cracks after endless sterilization cycles. Nearby stands an extracorporeal membrane oxygenator. Its hollow fibers are formed from flexible carbon polymers that withstand both warm blood and harsh disinfectants. Inside, carbon dioxide leaves the bloodstream and oxygen rejoins it, buying time for failing hearts to mend. In radiology, imagine a slim black table supporting a patient during a CT scan. That table is woven from aerospace-grade carbon fiber composite. Carbon's high stiffness allows the table to remain feather-thin, letting X-rays pass with little interference. Because carbon barely shows on images, physicians view clear scans without ghost shadows. Move deeper into microscale. Graphene oxide membranes are being explored to filter viruses from donated blood. Their one-atom-thick layers, punctuated by controlled pores, allow water and small ions through while blocking pathogens. Early trials hint at faster plasma purification, reducing wait times for transfusions. On the surgical tray lies a carbon-coated scalpel blade. A plasma deposition technique bonds diamond-like carbon onto stainless steel, creating an edge that stays keen through longer procedures. The smooth carbon layer lowers friction, producing cleaner cuts and reducing tissue trauma. Tiny flecks of carbon also coat orthopedic screws, lowering wear and shielding joints from metal ion release. Inside joint replacements, ultra-high molecular weight polyethylene is fortified with carbon fibers, resisting abrasion for millions of steps. In heart valves, pyrolytic carbon leaflets mimic natural tissue. Their glass-like surface rejects blood clots, letting valves beat quietly year after year. In oncology, carbon finds duty in carbon ion radiotherapy. Beams of charged carbon nuclei enter the body, travel with little scattering, then deposit nearly all their energy at a precise depth in the tumor. Surrounding tissues receive minimal dose, sparing healthy cells. Clinics in Japan and Europe have used this therapy to shrink cancers resistant to conventional X-rays. On the nanoscale, researchers attach anti-cancer drugs to carbon nanotubes that home toward tumors by following subtle chemical signals. Lasers tuned to near-infrared light then heat the nanotubes, releasing medicine only at the right spot. Trials continue, yet early studies suggest fewer side effects and stronger local impact. Even diagnostic wearables rely on carbon. A flexible graphene sensor printed on a thin polymer strip sticks gently to skin, monitoring electrical activity of the heart or measuring glucose in sweat. Graphene's conductivity stays stable when bent or stretched, allowing real-time data without bulky electrodes. From detox to imaging, from implants to targeted therapy, carbon quietly underpins modern medicine, helping bodies find balance and easing suffering with its unique blend of strength, softness, and chemical calm. 5.2. Technology and heavy industry. Shift now to the hum of factories, data centers, and power grids. Carbon carries human ambition into alloys, circuits, and soaring structures. Steel is iron infused with carbon. At roughly 2% carbon content, atoms of the element slot into spaces between iron atoms, locking the lattice tighter. Adjust that fraction slightly and steel transforms from ductile rebar to resilient spring, from razor-sharp blade to impact-resistant armor. Every bridge cable, shipping container, and skyscraper beam owes its strength to carbon's tiny interstitial presence. Inside foundries, coke, a nearly pure carbon solid derived from coal, fuels blast furnaces. Coke burns at more than 2000 degrees Celsius, and crucially, it donates carbon to molten iron, creating pig iron for further refinement. Without coke's high carbon heat, modern mass production of steel would falter. In the world of high-performance machining, tungsten carbide steals the spotlight. Tungsten atoms bond with carbon in a crystal harder than almost any natural mineral. Drill bits tipped with tungsten carbide bore through granite, slice into titanium alloys, and shape gleaming dentist tools. Move up to aviation. Wing spars in the latest aircraft contain layers of carbon fiber-reinforced polymers. Each fiber is a bundle of aligned carbon crystals, astonishingly light yet megapascal strong. Set in epoxy resin, they form composites that shave tons from an airliner's weight, saving fuel on every intercontinental flight. In renewable energy, carbon continues its quiet service. Graphite electrodes steer current in electric arc furnaces recycling scrap steel. Carbon-carbon composites endure within the throat of reusable rocket nozzles, surviving rapid shifts from sub-zero launch pads to fiery re-entry. Carbon foams act as lightweight cores in wind turbine blades, stiff without mass, resisting fatigue under decades of coastal gales. Inside lithium-ion batteries, graphite hosts lithium ions between its planar sheets during charging. When the battery discharges, lithium slips out, releasing stored energy. Anode scientists explore hard carbon and graphene foams seeking faster charging and longer life for electric cars. Hind Audio uses diamond-coated tweeter domes. The thin carbon layer keeps vibration accurate at ultrasonic frequencies, delivering crisp notes that sparkle in concert halls. In optics, chemical vapor deposition diamond windows transmit infrared laser beams without warping, critical for cutting steel in factory lines. At quantum scale, processors try to tame silicon carbide for qubits that run at higher temperatures than delicate superconducting circuits. Meanwhile, carbon nanotube transistors promise to shrink switch size beyond silicon's limits, operating with lower power and greater speed. Researchers have already built prototype CPUs containing 10,000 nanotube gates, hinting at a post-silicon era led once again by carbon. Even clouds of data lean on carbon. Massive server farms channel heat away through graphite heat spreaders. Thin layers of diamond-like carbon protect hard drive platters, letting read heads float nanometers above whirling disks that store centuries of text and imagery. From molten iron and rocket nozzles to quantum bits and music, carbon remains the versatile workhorse of technology, marrying low weight, high conductivity, and steadfast endurance. 5.3. Everyday life and familiar products. Finally, return to ordinary surroundings. Open a drawer, turn on a lamp, pick up a pencil. Each simple act is touched by carbon. Start with breakfast. The polymer spatula flipping an egg contains carbon black filler, making it heat-resistant and giving deep color. Your non-stick pan owes its slick surface to a carbon fluorine coating that shrugs off grease. The activated carbon filter in the refrigerator traps odors, keeping produce fresh. Commute along city streets. Tires contain finely milled carbon black, reinforcing rubber so that treads hold shape through summers and winters. Windscreen wiper arms use carbon steel springs. Brake pads blend graphite to dissipate friction heat quietly. Reach the office or school. The humble pencil leads back to 1564, when a storm toppled a tree in Cumbria and revealed a vein of pure graphite. Today's graphite cores are mixed with clay and wax, yet carbon still glides across paper, turning thought to visible language. Whiteboard markers use carbon black pigment for deep black ink. Inkjet cartridges mix carbon dispersions to print crisp letters that resist sunlight. Mobile phones hide carbon in many layers. Flexible printed circuits rely on graphite traces for ground planes. Touch screens include thin carbon-based adhesives bonding glass to display. Microphones use a historical heart of carbon granules in some legacy designs, though now largely replaced by capacitive sensors. Still, without carbon fibers reinforcing the plastic shell, a modern phone would flex and crack in pockets. At home, water flows through activated carbon cartridges, stripping chlorine and organic compounds so tea tastes clean. In closets, small charcoal sachets gather moisture and odors. Aquarium filters rely on granular carbon to capture tanning acids, letting fish thrive in clear water. Outdoor adventures carry carbon farther. Trekking poles, bicycle frames, kayak paddles, and tennis rackets made of carbon fiber composites balance strength with featherweight poise. Climbing helmets mix expanded polystyrene with carbon fibers to absorb impacts. Ski boots stiffen with carbon inserts that echo mountain ridges. In the arts, carbon breathes color and sound. Painters sketch with compressed charcoal before committing brush to canvas. Violin bows strung with horsehair may be crafted from carbon fiber sticks that resist changes in humidity. Modern pianos include carbon composite soundboards that hold pitch better than spruce. Health at home leans on carbon too. Toothpaste harnesses activated charcoal for gentle whitening. Breath mints hide carbon black dye to give licorice its depth. Many pharmaceuticals deliver active ingredients inside carbon-based capsules that dissolve at just the right moment in the digestive tract. Carbon also shapes fashion. High-performance denim weaves carbon fibers with cotton for abrasion resistance. Winter jackets line hoods with synthetic fur spun from carbon polymer strands, trapping warm air while shedding snow. Look at light. Some vintage bulbs glowed by heating thin carboniced bamboo filaments. Today, organic light-emitting diodes rely on carbon-rich polymers and small molecules to shine in televisions and mood lamps, painting living rooms with energy-saving color. Even taste is touched by carbon. Oak barrels charred on the inside lend whiskey its caramel notes. The char layer filters harsh compounds and adds smoky richness. Coffee roasted until dark owes its bold flavor to carbon-based Maillard products formed from sugars and amino acids. In every corner of daily life, carbon manifests as pigment, strengthener, sorbent, filter, flavor, or sound. One element, endless roles, always close at hand. A gentle closing reflection. Rest now, letting a calm breath in, a slow breath out. As you sit or lie, carbon surrounds you in walls of reinforced concrete, in fibers of blankets, in ink that printed these words. It waits in batteries powering lights, in circuitry guiding screens, in the very gene sequences inside every cell. Carbon is the backbone of medicine healing the body, the engine of industry forging our tools, and the quiet helper in ordinary routines. One element, four open bonds, infinite possibilities. Let that thought settle around you like a soft carbon-woven quilt. With each easy inhale, remember the element's kindness. With each gentle exhale, know that carbon carries a story of resilience and service, linking stars to hospitals, skyscrapers to morning tea, and your own breath to the rhythm of the entire planet. Curiosities and Mysteries. 6.1. Astonishing and little-known facts. 1. Diamond rain on ice giants. Travel in thought to the deep interiors of Neptune and Uranus. Pressures there reach millions of atmospheres and temperatures exceed thousands of degrees. Laboratory shock experiments and quantum simulations suggest that methane molecules split under those extremes, freeing pure carbon. The atoms lock into crystalline lattices and tiny diamonds begin to fall. Each crystal drifts for hours through a hot fluid mantle before melting again. No probe has witnessed the glitter directly, yet infrared spectra fit the theory, hinting at endless sparkling storms hidden beneath blue clouds. 2. Graphene moves electrons with almost no resistance. A single layer of carbon atoms arranged in a honeycomb lattice allows charge carriers to race at more than 1 million meters per second. Even at room temperature, electrons glide almost ballistically, as if the sheet were a frictionless highway. That speed, joined with mechanical flexibility, makes graphene a contender for future radio antennas, terahertz detectors, and ultra-fast processors that stay cool while operating at frequencies silicon cannot touch. 3. Carbon nanotubes are stronger than steel while weighing almost nothing. Roll a graphene sheet into a cylinder just a few nanometers wide and you create a nanotube. The bonds along its wall resist stretching far better than any metal. Gram for gram, a nanotube rope could hold 50 times the load of a steel cable. Engineers dream of a space elevator whose 20,000-kilometer tether is woven from such strands. The challenge is making tubes long enough and defect-free, yet each year synthesis methods climb another order of magnitude in length. 4. Fullerenes act as molecular cages. When researchers first struck graphite with an electric arc, they collected spheres of 60 carbon atoms shaped like soccer balls. These buckyballs can trap metal ions, noble gases, or radioisotopes inside. The carbon shell keeps its guest imprisoned for decades. Chemists now attach drug molecules to the outside and aim the ball at tumors, or load hydrogen inside as a safe, dense fuel. A single gram can hide over 400 liters of gas at ambient pressure. 5. Carbon aerogel swallows almost all light. A porous sponge of amorphous carbon, only a few millimeters thick, can absorb up to 99.9% of incoming radiation from ultraviolet to far infrared. Photons bounce within the maze of pores until converted to heat. Telescopes coat internal barrels with this material to stop stray glare. Solar thermophotovoltaic panels use it to trap sunlight that would otherwise reflect and be lost. The darkest man-made substance owes its inky color to carbon's chaotic embrace of light. 6.2. Unresolved questions and exotic phenomena. 1. Could carbon-based life thrive beneath Europa or Enceladus? These icy moons hide global oceans warmed by tidal flexing. Ultraviolet light cracks carbon dioxide on their surfaces, and plumes sampled by spacecraft reveal simple organics. Hydrothermal vents on the ocean floor might feed carbon-charged chemistry, much like black smokers on Earth. Future landers will drill or sip the rising spray in search of fatty acids, amino acids, or simple hydrocarbons that hint at metabolism sealed away from sunlight. 2. The missing carbon in interstellar dust. Starlight shows that a fraction of cosmic carbon is tied up in unidentified grains that neither graphite nor silicate models can explain. Astronomers suspect long, frigid ribbons of graphene or tangled amorphous carbon aggregates drifting through molecular clouds, invisible but for the way they dim distant stars. Polarization surveys with next-generation radio arrays may finally separate their signature from ordinary dust and close the inventory on where cosmic carbon really hides. 3. Lightning-borne fullerenes in Earth's atmosphere. High-altitude research planes sampling storm clouds found bursts of C60 and C70 molecules hours after heavy lightning. Laboratory arcs duplicating thunder produce similar clusters, yet the efficiency and global budget remain unknown. Do intense tropical storms seed the stratosphere with nanocarbon that affects ozone chemistry or cloud condensation? Climate models still lack this potential carbon feedback. 4. Subsurface carbonate lakes on Mars. Orbital radars have mapped circular deposits rich in calcium carbonate, overlain by frozen brine. Some geologists believe these rings mark extinct deep lakes where volcanic heat kept water liquid for millennia. If true, carbon cycled there from gas to rock to life-friendly solution 3 billion years ago. Future drills may uncover microbial fossils entombed in calcite, offering direct evidence of ancient Martian carbon biochemistry. 5. Black diamonds from space. Scattered across Antarctic ice lie pea-sized stones darker than coal yet harder than quartz. Electron microscopy shows they are diamonds laced with graphite and metal blobs, born in impact shocks outside Earth. No laboratory has fully reproduced their composite texture. These interstellar jewels hint at unimaginably violent collisions between carbon-rich asteroids elsewhere in the solar system, or perhaps in other systems entirely, flung here by gravitational pinball over millions of years. 6.3. Anecdotes and hidden history. 1. The graphite that recorded Waterloo. British artillery crews in 1815 penciled firing tables directly onto gun carriages, because ink blurred in drizzle and smudged under recoil. Graphite stayed legible through heat and mud. After the battle, historians collected the wooden planks. Pencil marks remained crisp, while ink notes on paper journals had run. Carbon kept the calculations that shaped the outcome when weather and iron tried to erase them. 2. The Scotch tape moment behind graphene's discovery. In 2004, a Manchester graduate student kept peeling sticky tape from a chunk of graphite, folding the tape and peeling again. After dozens of repetitions, only a faint gray film was left. Under an optical microscope, it showed a surprising blue sheen against the oxide layer of silicon below. That sliver was 1 atom-thick graphene. The experiment cost pennies but opened a billion-dollar race for two-dimensional electronics. 3. Edison's carbon autograph. During the opening of the Pearl Street Power Station in 1882, Edison unscrewed a prototype bulb, removed the carbonized bamboo filament, and scratched his signature on the inside of the glass. He resealed and evacuated the envelope, then lit it before the crowd. His carbon signature glowed in silhouette for hours, protected by vacuum. The bulb survives in a private collection, one of the earliest neon-like signs, written by pure carbon. 4. The singing diamond. Gemologists cooling large natural diamonds with liquid nitrogen, then warming them rapidly, hear a faint high-pitched ring. Microfractures in the crystal trap pockets of air. Thermal stress flexes those cavities, making them resonate like microscopic tuning forks. The sound is too soft for unaided ears but measurable with laser vibrometers. Jewel insurers use the acoustic fingerprint to detect internal flaws without cutting the stone. Carbon sings its hidden structure to those who listen carefully. 5. A carbon harp for the mind. In 1920, Italian researcher Libbio Barossi stretched thin carbon fibers between metal posts and passed millivolt nerve-like pulses through them. The fibers vibrated and produced audible tones, creating what he called a neural harp. The idea faded, yet modern headphone makers have revived similar carbon membranes, prized for low mass and uniform response. When music streams through lightweight drivers, you hear echoes of Barossi's forgotten experiment, where carbon translated electricity into song. Quiet closing reflection. Let these stories settle like dust under starlight. Carbon reigns as jewels inside frozen giants and drifts as charcoal flakes above Earth's storms. It captures poison in hospital rooms and records cannon angles on damp timber. It whispers in diamonds, thunders in meteors, and bends electrons to near-relativistic speeds. Draw one more steady breath. The carbon atoms entering your lungs have tasted the stratosphere, volcanic vents, graphite seams, and cometary ice. Soon you will return them to the air, and they will journey on, perhaps to a leaf, a lightning bolt, or a distant diamond cloud. Carbon is the restless storyteller of the universe, and tonight you share a page in its endless chronicle. Sleep well, held in the quiet resilience of the element that never stops exploring. Elemental Dreams and Sleep Descent. 7.1. Gathering Carbon's Quiet Images. Settle a little deeper into whatever cradles you. Notice your breath as a soft tide, rising, falling. Each inhale draws carbon dioxide in. Each exhale releases it again. The motion is so gentle you barely feel it, yet every cell listens. Imagine a black canvas of starlit space. From that velvet dark a faint glow emerges, the hush of an ancient charcoal ember. It flickers once, twice, then steadies into a warm red pulse. That ember is carbon in its most familiar form, carried from 1,000 winter fires. See the ember stretch and reshape, forming outlines of trees at dusk, their trunks built from carbon chains that have stood through seasons of wind and snow. Lantern light slants across bark, revealing fine grooves, rivers frozen in wood. Now the image shifts. The ember cools, brightens, and becomes a diamond. No longer dark but clear as frozen rain. Light moves inside, bouncing from facet to facet, casting tiny prisms on a velvet cloth. You can almost hear a crystalline chime each time the beam pivots. The diamond turns slowly, and with each turn, one of its facets reflects a scene. A graphite pencil gliding across a notepad, writing a word that only you know. Or a leaf unfolding in spring, its veins filling with sugars that carbon shaped moments before. A distant radio telescope, its dish blackened by carbon foam, listening for faint whispers among the stars. Each scene glows for a heartbeat, then fades, replaced by the next. The diamond does not hurry. Trusts time. The gem softens again. It unknots, unspools, and becomes a sheet of graphene, 1 atom thick, stretching out like a calm lake at dawn. On its surface electrons glide silently, swift as swallows. They leave no mark, only potential. Your thoughts rest atop that invisible highway, and you sense an easy current tugging you toward rest. Hold that picture a moment longer, then let it drift. The images of ember, diamond, and graphene dissolve into a gentle carbon mist, soft and safe. As the mist settles around you, feel your muscles unlace. Shoulders slide away from ears. Jaw loosens. Fingers uncurl. Breathe in. Carbon joins your blood, slips into cells, feeds the quiet burn that keeps you warm. Breathe out. Carbon carries away the day's concerns, releasing them to the night air. 7.2. Weaving carbon into the rhythm of sleep. Begin to notice a simple mantra threaded through breath. Hill. Stardust. Hill. Home. Whisper it in your mind if that feels good, or let the words remain unspoken, sensed as an undercurrent. On Stardust, draw in, filling every corner of your lungs. On home, release, feeling gravity cradle you more fully. As you continue, picture carbon atoms riding each breath like tiny lanterns. With every inhale, lanterns enter, glowing faint gold. They travel through branching tunnels of bronchi, then into alveoli, where thin membranes welcome them into blood. The lanterns drift along quiet rivers of plasma, past the steady drum of your heart, arriving at muscle, brain, marrow. They flicker kindly on arrival, offering energy and ease. When you exhale, a different set of lanterns departs, their glow now soft blue, carrying with them fatigue, stray tension, unused worry. See them float through the same tunnels back to open air. They join the hush of the room, then slip beyond walls into night. Somewhere a tree waits, its stomata opening like tiny mouths, eager to drink those blue lanterns at first light. Allow that exchange to continue without effort. Lanterns in, lanterns out. Stardust home. Stardust home. The rhythm slows naturally, matching the slower cadence of approaching sleep. Now call up 3 quiet sensations linked to carbon. The faint squeak of graphite on paper, as if someone is writing lullaby lyrics on your behalf. The muffled crackle of a campfire coal, steady and unhurried. The cool, almost weightless press of a carbon fiber shell, light yet protective, resting over your heartbeat. Let those sounds and feelings layer softly, then drift to the background like a distant chorus. They remain there, a gentle reminder that carbon knows both flame and silence, both strength and softness. Survey your body once more. Starting at toes, invite any remaining tightness to melt and follow the exhale. Ankles, calves, knees. Let carbon's adaptable nature become yours. In the way atoms pivot between diamond rigidity and graphite softness, allow your muscles to pivot from daytime alertness to nighttime release. Hips settle. Lower back smiles. Rib cage floats like a raft on calm water. Shoulders rest as leaves on still branches. Neck lengthens as tension flows away. Face slackens, brow smooth as polished coal. Tongue lies warm and flat. Your body now mirrors carbon's versatility. Solid where needed, relaxed where safe. 7.3. Drifting into carbon's eternal cycle. Envision a circle drawn from charcoal on parchment. The line is unbroken yet not static. See it slowly rotating clockwise, tracing seasons. At the circle's highest point you find a green leaf. Sunlight touches it. Photosynthesis begins. Carbon dioxide transforms into sugar. Move along the circle to the right. The sugar travels down the stem, becomes cellulose, lengthening a branch. Farther still, autumn arrives. The branch sheds its leaf, which tumbles to soil. Fungi and microbes break it down, releasing carbon back to air and earth. That carbon drifts until winter, when a silent snowfall blankets the forest. Beneath snow, seeds sleep, holding carbon in their shells. Spring returns. Seeds sprout, pull carbon into new leaves, and the circle completes. Now picture yourself inside that turning circle. Carbon flows through you just as surely as through forest cycles. A decade from now, nearly every carbon atom in your body will have been replaced by new ones, yet you will still be you. The continuity of self rests not in single atoms but in arrangement, rhythm, pattern. Carbon is the humble courier keeping that pattern alive. Begin to let the circle fade. In its place appears a deep night sky, not black but rich indigo. Stars shimmer. You recognize they are nurseries of carbon, forging atoms that will dance through eons. Choose one star. Imagine its light taking hundreds of years to reach your eyes. Somewhere in that beam may travel a carbon atom liberated by a stellar wind. One day it could drift into a cloud, seed a new solar system, settle into a planet, perhaps a leaf, perhaps a lung. That possibility feels boundless, soothing. The night sky dims further, edges softening. Awareness narrows to the gentle tide of breath. Stardust home. Lanterns in gold, lanterns in blue. Muscles fluid, thoughts slow. The boundary between body and room blurs. You float in a carbon lattice of comfort, strong yet weightless. Memories of ember and diamond linger like faint perfume, then gently recede. If stray thoughts arise, tasks unfinished, voices from the day, recognize them as carbon scribbles on a chalkboard. With one easy exhale, wipe the board clean. The chalk feels light in your mind's hand. Carbon yields, then clears, leaving quiet slate. Feel time stretch. Seconds lengthen into soft ribbons. With each ribbon, consciousness drifts a little farther toward rest. You are safe inside carbon's cradle, an element that has witnessed planets form and will outlive stars. It watches over your sleep without judgment, without hurry. Let go. No need to guide the breath anymore. Finds its own pace. The body knows what to do. Mind settles like charcoal dust on still water, slowly sinking, leaving the surface mirror smooth. Carbon carries the last whispers of wakefulness away, atom by atom, until only peaceful darkness remains. Dream softly, stardust pilgrim, while carbon keeps the world turning in silent, patient circles. Now, as our journey softly comes to a close, allow yourself a moment of quiet reflection. Feel how each calm breath gently connects you to the element we've explored tonight, one tiny piece in the infinite mosaic of the universe. As you drift gently toward rest, picture your thoughts like atoms of the element we've visited today, floating serenely through the vastness of your imagination. Just as elements combine, transform, and quietly support all life around us, your mind now settles, combining peace with tranquility. Remember how every atom within you once journeyed through stars, oceans, and forests, cycling endlessly through the great natural symphony. Tonight's element, in its silent and humble way, is part of that eternal flow, gently sustaining the heartbeat of existence itself. Think of the wonder we share. This quiet exploration, this peaceful communion with matter. With each soft exhalation, you return the element back into the embrace of the world around you, an invisible yet profound exchange. You are part of this endless rhythm, connected in every silent moment, every restful sigh. Imagine the element we've discovered tonight, existing beyond time, beyond human stories, gently present long before us, and quietly continuing long after. It carries the memory of ancient worlds and dreams of futures yet unseen. You too hold this gentle eternity within each breath. Allow yourself now to float gently, as if carried by the element's invisible hands, toward restful sleep. Feel comforted by knowing that the universe generously shares every atom, every molecule, every peaceful moment with you. Let your eyelids grow heavy, your thoughts softly dissolve like mist at dawn. Know deeply that you belong, gently cradled in the elemental harmony of the cosmos. May your dreams tonight be filled with quiet wonder and peaceful exploration. Rest now, knowing you are safe, cherished, and connected to this gentle element, to this gentle earth, and to the vast, beautiful silence of the universe itself. Good night, and rest peacefully, embraced by the elemental calm of night chemistry.